Imagine waking up a billion years from now to find that every star in the night sky, save for those in our own galaxy, has vanished. No distant galaxies, no cosmic neighbors, nothing but an infinite black canvas stretching in every direction. This isn't science fiction, it's the terrifying reality we would face if the Milky Way were ejected into a cosmic void. But here's what makes this scenario even more chilling. It may have already happened to countless galaxies across the universe, and we would never know. They exist in absolute darkness, their astronomers completely unaware that billions of other galaxies lie just beyond an unreachable horizon. The galactic neighborhood. To understand cosmic exile, we first need to understand cosmic community. The universe isn't uniformly filled with galaxies. It has structure, architecture, neighborhoods of unimaginable scale. Our Milky Way resides in the local group, a gravitationally bound collection of approximately 80 galaxies spanning about 10 million light-years. This group is dominated by three large spirals: the Milky Way, containing 200 to 400 billion stars, Andromeda, or M31, roughly 1 trillion stars, and the Triangulum Galaxy, or M33, around 40 billion stars. The rest are dwarf galaxies, small, dim collections of stars orbiting the larger members like cosmic satellites. But the local group itself is just a small neighborhood in a much larger metropolis. We're part of the Laniakea supercluster, discovered in 2014 through detailed mapping of galaxy motions. This immense structure contains approximately 100,000 galaxies with a total mass of about 10 to the 17th solar masses, stretching across 520 million light-years. The Laniakea name comes from Hawaiian, meaning immeasurable heaven, a fitting description for something so vast. Laniakea itself is connected to other superclusters through filaments and sheets of galaxies, forming what cosmologists call the cosmic web, a foam-like structure of matter that permeates the observable universe. The empty spaces between. But between these dense regions of galaxies lie the voids, cosmic deserts that dwarf even the largest galactic superclusters. The Boots Void, discovered by Robert Kirshner and colleagues in 1981, remains one of the most striking examples. This nearly spherical region spans approximately 330 million light-years, about 100 megaparsecs in diameter. In a volume that should statistically contain around 2,000 galaxies, astronomers have found only about 60. That's a 97% deficit, a cosmic ghost town. But Boots isn't alone. The giant void in Cain's Benatisi spans roughly 1.5 billion light-years. The KBC void, named for Keenan, Barger, and Cowie, is even more controversial. Some researchers suggest we might actually be living near the center of a void 2 billion light-years across, though this remains highly debated. These voids aren't completely empty. They contain some dark matter, wisps of intergalactic gas, and the occasional lonely galaxy. But compared to the dense galactic clusters, they're as close to nothing as the universe gets. The average density in a void is about 10% of the universe's mean density. Imagine a city where 90% of the buildings have been removed, leaving only scattered, isolated structures. How voids form. Voids are actually a natural consequence of cosmic structure formation. In the early universe, quantum fluctuations created slight variations in density. Denser regions attracted more matter through gravity, growing denser still, while less dense regions lost matter to their surroundings, becoming ever more empty. This process, amplified over billions of years, created the cosmic web, dense knots of galaxies connected by filaments with vast voids between them. The voids are essentially regions that lost the cosmic lottery. They started slightly underdense and have been emptying out ever since, as galaxies at their edges get pulled toward the denser regions surrounding them. Gravitational slingshots. The most likely mechanism for galactic ejection is a three-body gravitational interaction. When three massive objects interact gravitationally, the system is chaotic and unpredictable. Often, one object gets ejected at high velocity, while the other two become more tightly bound. In galactic terms, imagine the Milky Way passing through or near a dense galaxy cluster. The combined gravitational pull of hundreds or thousands of galaxies could accelerate us to escape velocity, the speed needed to break free from the cluster's gravitational pull entirely. The mathematics here are brutal but elegant. Escape velocity from a galaxy cluster can be calculated using v escape equals the square root of 2gm over r, where g is the gravitational constant, m is the cluster's mass, and r is the distance from the cluster's center. For a massive cluster like Virgo, mass 10 to the 15 solar masses, the escape velocity at the outskirts is around 1,000 to 1,500 kilometers per second. If a close encounter boosted the Milky Way to these speeds, we'd be on a one-way trip into intergalactic space. Real examples of hypervelocity galaxies. This isn't purely theoretical. Astronomers have discovered hypervelocity galaxies, systems moving so fast they'll eventually escape their clusters entirely. In 2016, astronomers discovered a galaxy moving at 2 million miles per hour, about 900 kilometers per second, relative to its cluster. In 2019, researchers found an ultra-compact dwarf galaxy fleeing the Virgo cluster at 1,400 kilometers per second, fast enough to escape the cluster's gravity permanently. These discoveries prove that galactic ejection is real and happening right now across the universe. Most hypervelocity galaxies are small dwarfs, but there's no physical law preventing a large spiral like the Milky Way from being kicked out under the right circumstances. The alternative, galaxy harassment. Another mechanism is galaxy harassment, repeated high-speed encounters with other galaxies that progressively strip away a galaxy's outer stars and gas while gradually increasing its velocity. It's like being mugged repeatedly until you're both broke and running for your life. Each close passage transfers momentum and can also strip away the galaxy's dark matter halo, making it less gravitationally bound to its neighbors and easier to expel. After enough encounters, the cumulative effect could send the galaxy careening into the void. The journey timeline. Let's map out the physics of the journey itself. Assume the Milky Way gets ejected at 1,000 kilometers per second, a realistic velocity for a cluster escape. At this speed, we'd travel about 1 megaparsec, 3.26 million light-years, every 3 billion years. The Boots void is about 100 megaparsecs across, meaning it would take roughly 300 billion years to traverse completely, longer than the current age of the universe. But we wouldn't need to travel that far to experience cosmic isolation. The effects would begin much sooner. Million years 0 to 100, the imperceptible beginning. Initially, nothing would appear to change. The night sky would look essentially identical. The nearest galaxies, Andromeda at 2.5 million light-years, the Magellanic Clouds at 160,000 to 200,000 light-years, would remain visible and seemingly stationary. However, sensitive instruments would detect changes. The spectral lines from distant galaxies would show increasing redshift, not from the expansion of space alone, but from our motion away from them. Peculiar velocities would become apparent. Million years 100 to 500, the distant fade. The first casualties would be the most distant galaxies visible in our surveys. These systems, already at the edge of visibility for our telescopes, would redshift into invisibility. Their light, already stretched by cosmic expansion, would be further stretched by our recession velocity. The combined effect is additive. If we're moving away at 1,000 kilometers per second and the universe is expanding, galaxies at certain distances would experience total recession velocities exceeding the speed of light, once you account for both our motion and expansion. At that point, their light can never reach us. They've crossed our cosmological horizon. Million years 200 to 10,000, the emptying sky. Now the visible changes accelerate. The major galaxy clusters, Vermo, Coma, Fornax, would fade from view. These structures, containing thousands of galaxies each, would simply vanish from the sky as their light redshifts beyond detection. Amateur astronomers would notice the loss. The Virgo cluster, visible in modest telescopes as a collection of fuzzy spots in the constellation Virgo, would dim and disappear. The great galaxy catalogs, Messier, NGC, IC, would need massive revisions as object after object became unobservable. Million years 10,000 to 100,000, true isolation. We are now truly alone. Every external galaxy has redshifted beyond detection. The cosmic microwave background, already faint at 2.725 Kelvin, would be